Hello and welcome to the VHDL data types lecture. In this lecture, I'm going to cover some of the commonly used data types, specifically the ones we'll be using for the projects in this course. We'll be covering the standard logic vectors, unsigned versus signed, as well as integer data types. The first one we're going to cover is the standard logic data type. A standard logic data type represents one bit of data, if you will. You have several values it can represent, which are x, which is unknown, a 0, which is a logic 0 or ground, and a 1, which is a high or a logic 1 in digital, or z, which is a high impedance or like a tri-state buffer. And that typically won't be used unless you're working with an in-out, or you have a bus that's shared and multiple things could be driving it. You will possibly go to the z state. And a standard logic is represented with the keyword std underscore logic for standard logic. And when you're assigning values to a standard logic data type, you want to use a single quote. So for example, if you have a standard logic data type A and you want to assign it the value of 1 or a high, it would be a single quote, 1, and then and the single quote. The next data type we're going to represent is the standard logic vector, which is effectively an array of standard logic types. So if you have 10 standard logic data types, you can make a standard logic vector, which is just an array of that. And the standard logic vector can be any size. You define that when you define the data type. You'll say standard logic vector A is a standard logic vector from 27 down to 0. So you have bits 27 to 0, or 28 different standard logic data types. And the keyword for a standard logic vector is std underscore logic underscore vector, vector. And then inside that parentheses, you define the size of the standard logic vector from the starting bit, and then use the keyword down to the ending bit to give you the size of that actual vector. And when you're assigning values to a standard logic vector, you want it to be with double quotes. So if you have a standard logic vector that's a width of 3, and you want to assign it all zeros, you would use a signal assignment, and then you would do a double quote 0, 0, 0, and double quote, and that will define all 3 bits in that standard logic vector as all zeros. Just like the standard logic vector can represent has the same values. You can do x, which is unknown. You can have a 0, which is a low, 1, which is a high, and z, which is the high impedance or the tri-state buffer. So now that we understand the standard logic and the standard logic vector data types, let's take a look at some of these examples. So the standard logic vector example, if we'll put here, say, standard logic, and let's define it. So we're going to define it as a signal, and we'll call this signal sig underscore a, and we'll give it the data type standard logic by using the keyword std underscore logic, and then we'll give it an initial value of 0. So we want to use the single quote and give it a 0, and then end the semicolon. So this creates a signal, and the name is sig a, and it's a data type standard logic, and we give it the value of a 0 or logic 0. Let's create a second signal. We'll call it sig b, just for simplicity, and we'll make it a standard logic data type as well, and we're going to give it a value of 1. So we'll go ahead and put a semicolon to end. So now we have signal A, which is a standard logic data type, which has a value of 0. We have signal B, sig B, which is a standard logic data type of value 1. So if we want to start assigning values, we can make signal A, if we want to make that a 1, we would use a signal assignment and give it the value of 1. So now our signal A has a value of 1, or is a high. We can make it have a value of 0 by just doing the same thing, except put a 0 in our parentheses. Or if we want to give it a value of another signal, so we'll say signal A is given the value of signal B, and then a semicolon. So these are the different ways in which you can represent your standard logic. You can assign it a 1 or a 0. You can assign it the value of another signal, which would be your sig B, which has to be a standard logic. You could also assign it an element out of a standard logic vector. It just, the widths have to match. These are a width of 1, so it has to match the value that you're actually assigning it. The next data type we're going to look at a little bit here is we have the standard logic vector. And these are probably, the standard logic and the standard logic vector are probably the most common used data types in VHDL. Almost every design you work with will have a standard logic or a standard logic vector. So for a standard logic vector, we'll say signal, and we'll call it sig C, and we'll give it the standard logic vector. And now we need to define the width, or how wide is our standard logic vector. And I'm going to say this is from 5 down to 0. So that tells me that I have 6 bits. So I need to assign it 6 values. And if I want them to be 0, I have to do the double quotations, and I will go 1, 2, 3, 4, 5, 6. So I have 6 zeros, which represents the 6 bits that I have defined here. So I have a signal C, which is an array of standard logic values, or a standard logic vector of 6 of width 6, and every bit in there is equal to 0. I'll go ahead and close it. I can also do another keyword called others. So if I have sig D, we'll call this, and we'll make it a standard logic vector as well, standard logic vector, and we'll make it from 5 down to 0, and give it the initial value. I want all the values to be 1. So what I could do the following, and that would make all the values equal to 1. However, instead what I'm going to do is use the others keyword. So if I do, say, others, and I will assign them the value of 1 because I'm accessing them individually, close the parentheses, that will make every one of the 5 bits, or excuse me, every one of the 6 bits in signal D to a logic high or equal to a value of 1. So I will then go ahead, and if we have signal C, we can make it equal to the value of signal D, because signal C and signal D are both 6 bits wide, or a width of 6, so this statement is valid. I can also do access individuals. So if I want to access an individual bit in my signal C, I will access my bit 3. Now, if you want to access the least significant bit, you would go 0, or you can go up to 5. So I'll say, for example, sig 3, bit 3 is equal to, and at this point I could assign it equal to sig A or sig B because they're 1 bit wide, and I'm right here, my sig C, when I select the bit 3, it's a width of 1. So I can make it equal to sig A, or I can make it equal to sig B, or I could also make it equal to signal D. However, I have to pick a single value. So I can make it equal to signal D bit 1 if I wanted, and do a semicolon to end that statement. The next part we're going to look at here is, so next we're going to talk about the unsigned data types. An unsigned data type uses the syntax unsigned, which is just spelled out UNSIGNED, so unsigned. They're very similar to a standard logic vector in that you can access the bits individually, as we've seen, and when you initialize values or give it a value, you have to do the double quotes, very similar to the standard logic vector. However, the difference with an unsigned data type is that you have access to use the addition, so you can do an unsigned data type and say +1 to do, or you can take 2 unsigned data types and add them together to get a third unsigned data type. Where standard logic vectors, you don't have that freedom. You can't do simple additions like that. It doesn't allow you to do that. So that's kind of the advantage of using an unsigned data type. And these can only be used to represent positive numbers. If you want to represent negative numbers, you have to use the second data type, which is the signed data type. And a signed data type allows you to use or represent negative numbers. However, when you're representing negative numbers in the signed data type, it represents them in the 2's complement form. So it's not as simple. The bits don't exactly represent. So you'll take a number in binary and do the 2's complement of it to get the negative number. So I'll show you an example of how we do that. But just like the unsigned data type, the signed allows you the ability to use the addition, subtraction, as well as the greater than or equal to. If you want to go in like an if statement and do comparisons like that, it's great to use it for that. So it has advantages over the standard logic vector data type. And let's go ahead and take a look at some examples. So if we have let's look at first the unsigned data type. So we'll say the unsigned, make a comment here, so double dash, unsigned, and we want to create a signal. We'll say signal, and we'll call it sig e, and we will give it the unsigned keyword, and we will make it from 3 down to 0. So very similar to the standard logic vector, we represent it in the same way. So unsigned is from 3 down to 0, and then we have to give it an initial value. So just like we did with the standard logic vector, we can use this others keyword. So we will say others, and we will make it assign the value of 0. So we have this signal E, which is represent as a 0, and then we're going to do a signal F. So we use the keyword signal, call it sig F, and this will also have the unsigned. And just like before, we'll make it 3 down to 0, so it's four bits wide. And we are going to give it a value of 0, 0, 1, 0, which, knowing that we can only represent positive numbers, is a positive 2. That's the value we're representing. So if I want to, let's say for example, take my sig e and I want to make it equal to a 0. Now it's already equal to a 0, but I can do the others keyword, so we'll say others, and I can then assign it either a value, all values of 1, or all values of 0. So we'll make it a 0 again, and that makes our sig e a 0. We can also do the addition. The addition operations are now valid using the unsigned data type. So our sig e is equal to our signal F, and we'll say plus 1. So our signal F is a value of 2, and our signal E is now equal to the signal F plus 1, so it's 2 plus 1. Our signal E is now equal to a positive 3. The next data type we'll kind of review here is our signed data type. The signed data type, it uses the keyword signed, so we'll say signal signed, and just kind of like our unsigned as well as our standard logic vector, we want to give it we have to give it a size. So signal, we'll call it sig g, and we'll give the keyword signed, and we're going to make it from 3 down to 0, and we'll give it a value of, we will use the others just like we did up here, so we can copy our others and paste. So now we have a signal g, which is equal to a value of 0, because in 2's complement, all zeros is still 0. So now if we do a signal h, and we are going to give it the signed as well, and we will make it from 3 down to 0. And this one we're going to assign it to a -5. So a -5 in 2's complement, you need to know the number of bits. So we need to represent a -5 using 4 bits in 2's complement, which is equal to a 1, 0, 1, 1. And we'll put our semicolon there. So this is equal to a -5. So in order to show you kind of how This works if we take our signal G and we can assign it use our others assignment, so we can make it equal to a 0, even though it already is a 0, but we'll just assign it to a 0 again. We can do assignments like this. We can also do another signal. We'll say our signal H, and we will now make that equal to our signal G plus 1. So our signal G is equal to 0, and we're adding 1 to it, so now our signal H at this point is equal to a 1. We could also do subtraction, so we could subtract a 1. If we would subtract a 1, then our signal H would now be equal to a -1. And that -1 will be represented in 2's complement with 4 bits. And so that kind of shows you how to use these standard logic as well as the unsigned and signed data types in VHDL. Next thing we're going to want to do is figure out, now that we know what the standard logic is, the standard logic vector, the unsigned and signed, let's take and represent these in our Vivado project. Now that we have the project open, let's assign the data types to our project in Vivado. So we know that we have the standard logic vector, unsigned and signed data types. So if we look at our project, we have our number buttons, which we've defined as an integer, our LED out, which we need to define, give it a data type. So we're going to give it the standard logic vector data type, and that's because we want to use this generic num buttons. So we'll say standard logic vector, and we'll use num buttons, and we will say -1 and go down to 0. So that's going to be the size we define our LED out. Now our button in is going to be the exact same as our LED out. So we can copy from our standard logic vector num buttons -1 down to 0, and we'll go ahead and paste. So that makes our LED out and our button in the same exact size, which is what we want, and this is defined by our generic num buttons. So now our enable, we need to give a data type, which we know a single bit is represented as a standard logic. So this defines our entity. We have our entity completely defined with our generic and our port, as well as the data types and sizes of all of our inputs and outputs for our button LED project.